Good day, grade 12 learners. Hope you are fine this afternoon. Welcome to today's Physical Sciences live session, proudly brought to you by Pagama Research and Development in collaboration with the Free State Department of Education. My name is Temba Ngobe. So today we are focusing our attention still on the paper one, which is a continuation of the lesson that we had same time last week. So we want to exhaust question 9 in paper 1, which is based on electrodynamics, right? So last week, just to recap on what happened, last week we managed to look at motors and generators. We looked at the principles that actually underpin, or the fundamental principle on which both motors as well as generators operate. So we agreed that the motor effect is the main concept around how a motor functions. We also spoke about the energy conversion, which has to do with electrical energy being converted into mechanical energy. So for a motor to function, we actually agreed that we have to have some energy input in terms of electrical. Okay, it can either be alternating current, then it's an AC motor, depending on the use. It can be direct current, then it's a DC motor. Then we further went to look at your generators, and we agreed that the fundamental principle on which the generators operate is the Faraday's law of electromagnetic induction, whereby the energy conversion that takes place in these types of machine is your mechanical energy, which gives us the electrical energy, right? So electrical energy is in the form of alternating current in the case of an AC generator, or DC current in the form of a DC generator. So we went on to put the two machines side by side and compared short differences and similarities by saying, okay, this is the uses or the applications of motors, this is the use or the application of generators. So the long and short of what we want to achieve at the end of today's session is that we want to look at the alternating current, right? Every other concept that relates to alternating current, which obviously has a lot to do and everything to do with alternating current generators. Then one would ask a question as to why is alternating current so important in our everyday lives. This goes on to speak to applications. Now, as I'm doing this live broadcast, the source of energy is electrical energy. The studio is live. There's lighting. There's everything. Now, that simply means that there must be an AC generator that ESCOM uses to generate electricity, which is fed into the grid, right? Now, this is very important because we're also in the age where there is an energy crisis within our South African context. So today's lesson is more of the real life application of electrodynamics than anything else, right? With those few, opening remarks, I just want us to go straight into the content and also reflect on what is important so that we take it from where we ended last week so that we complete the part on electrodynamics. So the key focus is on alternating current, right? Okay, now the weighting for question 9, paper 1, physics focus is the 55 marks, right? Now this 55 marks has got, number 1, has got electrostatics, right? Okay, it has got electric circuits, and then it has got electrodynamics, right? So if you check, it says electro, it means it has to do with the electron, right? Electrodynamics, which has to do with the motors and generator or electrical machines. So the 55 marks is a total of those three. So electrostatics will be typically your question 7 in section B, electric circuits will be question 8, and then electrodynamics will be question 9, right? There are only 10 questions in the first paper, right? So this is the second most weighted knowledge area. So the knowledge area is electricity and magnetism, right? Of which electrodynamics talks about the combination of electricity and magnetism, because the two cannot be separated, or one cannot exist in the absence of the other. Okay, electric circuits, we're talking about electric current, where we talk about the moving charge in a conducting material, which is electrical energy, right? And then electrostatics, we're still talking about the charge, which is the elementary charge or particle, which is the electron. But here we're talking about static electricity, which speaks to your charge at a point. We talk about electric fields and electric field at a point. Right. So this is just the broad overview of electricity and magnetism as a broader knowledge area. Right. Okay. Now we spoke about the different components of electrodynamics. So electrodynamics or electromagnetism, it's where magnetism is studied in conjunction with electricity because they coexist. So our intention today is to look at more of AC generators, because that's the one that gives us the AC graph, and also it speaks to the root mean square voltage and root mean square current. But we'll also look at what we call purely resistive circuits. Okay, we'll look at what is called purely resistive circuits. Okay, right, that's our intention for today. Okay, now the exam guide would often be used as a guide, or as a checklist for what is it that we need to achieve by the end of the session. And when we say to ourselves we are adequately prepared for the National Senior Certificate, let alone the trial exam, okay, let alone the mock exam, which you are going to write, in a few days' time in preparation of the trial exam. Right, this is the checklist. You must be able to state the advantages of AC over DC. So we prefer alternating current versus direct current. Okay, so our preferred is alternating current. Why is alternating current is important? Because there's something special about alternating current which relates to its everyday life application. Now, when you look at alternating current can either be stepped up or stepped down depending on the need. So if it's for household use, we step it down. If it's for large scale industry, manufacturing, processing, we scale it up. And it's easy to transport alternating current. It's easier and cheaper. So the pylons that you see, across the landscape of our country are actually those high voltage, low current cables that transmit from the power station to the substation, from the substation to the transformers, that goes into our schools, hospitals, and home. Okay, then we also have to be able to sketch the graph of voltage versus time, current versus time. This is for an alternating current circuit, right? Then we must be able to define the term root mean square voltage as well as root mean square current. So we've got VRMS as well as IRMS. So the examiner is saying the root mean square voltage, which is the potential difference, is the AC potential difference. So root mean square voltage or current, it is the AC current or AC voltage, depending which one of the two we are referring to. So this is for an AC, okay, which dissipates or produces, okay, the same amount of energy as an equivalent DC, right? Remember, when we talk about alternating current, it fluctuates between peak, which is the maximum, zero, peak in the opposite direction, because it changes direction every half cycle. So what is supplied or what is delivered to an appliance when you plug an appliance into the mains is the root mean square, or is the average. It's not the peak current, neither is it the zero or the lower peak in the other opposite direction. So it means what happens is that the current fluctuates between maximum zero and maximum in opposite direction. So what is delivered, because this happens at a very high frequency, when this happens, what is delivered to the appliance is the root mean square voltage or root mean square current, which gives the same amount of energy as that of equivalent DC source, right? So if we speak of the root mean square current, it is the alternating current which dissipates the same amount of energy as the equivalent direct current source. So it means for root mean square voltage, we are talking about the energy, that AC potential difference, which produces the same amount of energy as the equivalent. So I'll explain this using a graphical representation, because we know that DC current and DC voltage is constant. It doesn't change in magnitude. Why is it so? Because it's a direct current source, right? Now, when that happens, that direct current source provides, gives, or dissipates or produces a certain amount of energy. Now, what happens is for an AC, for it for us to refer to it as the root mean square current or root mean square voltage, we must compare it to that constant direct source of potential difference or current. That's why it is of the AC. Why AC? Because AC fluctuates, right? And then we also want to be able to solve problems. Pay attention to the subscripts in this formula, okay? Pay attention to the subscript. We don't just talk of current. We talk about current root mean square, okay, or root mean square current, or we talk about the peak current, which is the maximum. All these are for your. If we also talk about V max, which is the peak voltage, okay, all these are for an AC generator, right? Okay, so the examiner is very, very particular when it comes to the formula. So the data sheet that is provided would give you the detail of the subscript. So pay attention to that. When you copy the formula sheet, make sure that you copy it correct, because it's provided. I think it's the easiest it can get. And then we also want to solve problems using average power. So average power relates to average current and average voltage. All right. And then this is for a purely resistive circuit. I've mentioned this term before. What do we mean when we talk of a purely resistive circuit? If I plug a kettle into an AC source, which is the mains or the plug that an ordinary plug. Now, I create a circuit by so doing, whereby the source of energy is not a DC source, it's an AC source, which we have something of this sort. So if we have something like this, it means the source is an alternating current source. And then previously, we had something like this, which is a DC source, two opposite terminals. Okay, so if you connect the voltmeter, now here we are measuring the terminal potential difference. Okay, this is the terminal when connected to a circuit, potential difference. Okay, now when you connect a voltmeter across that AC source, what we measure there, this terminal potential difference in this case would be your VRMS, which will be delivered to a circuit. So if we plug a kettle into the mains, we are creating what is called a purely resistive circuit, because an appliance is a resistor. A kettle transforms or converts electrical energy into heat as it boils the water, whatever the case may be. A speaker is a resistor. So if you plug a speaker into a circuit where it produces sound, it means that speaker is a resistor. And then the circuit that would have created in that process would refer to it as a purely resistive circuit. So these are real practical circuits that we create when we plug any appliance into the mains. Okay, right. Now that's the exam guide. Now this is the data sheet that I've been speaking to. Very, very important. Why is the data sheet important? It gives us the whole range of formulae. Take note, instead of writing P is equals to VI, we're supposed to talk about the average power, because it speaks to the average current, which is the root mean square current. Equally so, it speaks to the root mean square voltage, because the word mean is in the measure of the central tendency would be taken in the context of average. Okay. So if you say P is equals to VI, this formula looks very, very familiar from ordinary circuits that we were looking at based on question 8. But in this case, we talk about the average power dissipated by an appliance, which is based on the average voltage as well as the average current. So pay attention to that, right? So this is the formula again for determining either VRMS or peak voltage. This is the maximum voltage. So peak means maximum. So the term peak, pay attention to that. It will refer to the maximum, be it the case of current or potential difference. Right. So the data sheet, you need not to go through the pain or the struggle of trying to memorize the formula, because at the end of the day, they shall be provided for your use. Okay, just know which one to use, under what circumstances, and why. Right. Okay. Hence, the title there says alternating current. This is about alternating current. So we'll use this for purely resistive circuits. Okay. Okay. All right. We'll look at practical examples of that. Okay. So let's look at where alternating currents fit. Last week, we looked at electrical machines, motors, and generators, right? So today, we're looking at alternating current. So this is the last bit of electrodynamics. Last week, we also spoke about the pre-knowledge, what exists around the current carrying conductor, which also served to, kind of highlight to us a very, very important concept, which says there can be electricity without magnetism. Hence, we are stuck with electromagnetism. Okay, right. So we spoke about the generators. We agreed that there are two classes of generators, which is a DC generator and an AC generator. Okay, so an AC generator is the one that has got the slip rings, right? It has got the slip rings. Okay, so be able to distinguish. So this is where we are going. If we are going to have a graph of potential difference versus rotation or versus time, we'll have, depending on the initial position, we'll have something like this. That's one cycle. Okay, that's another cycle. Whereas this one has got that double C, which we call the split rings. So take note of the terminology. So the split rings is a double C, meaning it's for a DC type of a generator. So our focus for today is the type of generator that has got slip rings, which produces or that gives us the alternating current. So this is the peak voltage. Peak voltage is just that it's the same magnitude but in the opposite direction. That was 0 voltage. So hence we call it the alternating, because it fluctuates between maximum 0 and maximum in the opposite direction. It alternates in that way. Then we know that for a DC source, we have something like this. The direction of current or potential difference does not change. So that's one cycle. Then 1.5, then there's 2 cycles as an example. Okay, so this could be voltage or EMF induced in volts versus time. This can be current in amperes versus time in seconds. So you must be able to distinguish between the two types of electrical machines, right? Okay, we know that a DC generator consists of a magnetic field, which is a result of what we refer to as those two pairs of magnets. Okay, so suppose that's our north pole, right? And then that's our south pole, something of this sort. Okay, so what exists here is an invisible magnetic field. Okay, hence we say it consists of a permanent magnetic field as a result of the magnet. So if we place a coil in a magnetic field, and then the two halves of split in the commutator, it will give us the direct current that we are referring to. So here is what I'm talking about. It just matches there. If you check, it's from north to south. That's the direction. And then this component is the one that allows us to say, what is the gender of this generator? Because of this double C, okay, it suggests, therefore, that it is a DC generator, which is not of particular interest to us for today. But it's very important for us to bring it so that we are able to show differences and similarities between the two types of electrical machines. Right. Okay. Now, I'm not going to spend a lot of time on the DC generator. This is how it actually functions. The split rings, they rotate every half cycle. They ensure that the direction of rotation is this of current is the same, because after every 180 degree turn, they changes the direction, meaning that if we rotate it in one direction, the current that is produced is in the same direction. So it will also fluctuate between maximum and zero, but in the same direction. Right. Now, here is the graph that we were referring to when we spoke of ADC. Now, let me just bring something in terms of the common errors that the examiner has actually identified over the years when it comes to a DC generator. Right. The SI unit of time is not the minute. If we talk about time, SI unit, we're talking about a second. And now one would ask, how long is a unit of time? If we talk of a unit, we're talking about one. Okay. So if we talk about, let's say, the number of cycles per unit time, we're talking about how many complete revolutions are there on the coil in 1 second. That's very, very important to actually understand that. Okay, I'll tell you why. The 0.025 is not the period, it's only half the period, because this is half the revolution, then this is a full revolution. In other words, this is 0, there's 90 degrees, that's 180 degrees, that's 270 degrees, and then that's 360 degrees. So the time that it takes for this generator to complete a single revolution is 0.05. So if you're given the number of rotations per unit time, you're able to determine the frequency. You are able to determine the period. So frequency, number of cycles per second, okay, which is a hertz. So if we've got a frequency of 1 hertz, what that simply means is that the coil makes one complete revolution per second. So if we say it's 50 hertz, what that tells us is that it's 50 cycles, complete cycles per second. Okay, and so on. Okay, now from a wall socket, let's say the 220 volts is what is supplied. Okay, you will always get the root mean square values which relate to the average power. So the average power is based on the root mean square values. Root mean square value of current, root mean square value of potential difference or voltage, which is the mean. Okay, this will produce the same amount of energy as an equivalent DC source, because essentially that is what is delivered to the appliance from the AC source. Okay, all right. The issue of graphs, we'll look at it. It's fine. Now, this is a DC generator. The output we're explaining, when do we get 0 volts? When do we get maximum? 0, maximum 0. So this current or potential difference is in the same direction, which is not of particular interest for us today. Ours has to do with the AC. Right. Now, as I've indicated earlier, I think it's equally important for us to also compare the two. Now, I wanted this to be a homework, but I felt it's important that we take a discussion so that it guides you when you do more homework or practice activities. Fine, we'll take a discussion on this. It says here, the current versus time graphs from two different sources are shown in the following diagrams, A and B, right? So these are time current graphs for different sources, okay? There can be only two sources according to our knowledge. There can be either a DC source or there can be an AC source. Okay, now the first question says, name the types of currents shown in diagrams A and B. Now, take note, this is 2 marks. What that simply means is that you have to name the source for graph A, whose output is graph A. Number 2, you have to name the source whose output graph is shown or illustrated in diagram B, right? So it's 1 mark for each. It goes without saying. Okay, so and you must be specific. Now, this current stays the same in terms of magnitude. Let's say if this was 10 amperes, it means it's 10 amperes throughout. Okay, this can only be possible from a source that is called a direct current source. Okay, so the name of the source is a direct current source. Now, but the output, the name type of current for A is direct current, simple. Okay, and then for B, because it fluctuates between maximum 0 and maximum in the opposite direction, this tells us that this is alternating current, right? But you must write it in full. Then the problem starts. Calculate the frequency of the current shown in diagram B. Frequency can only happen where we can actually analyze a graph or a cycle. Now, for direct current, the frequency there is for us from the graph is difficult for us to determine the frequency. We can calculate the frequency for B. Now, the question is, how many complete cycles do we have? Let's trace it. From here, we go up, come down. That's half a revolution. That's a full cycle. Okay. So in other words, there's 1.5 cycles. Okay. So frequency is equals to number of cycles, okay, divided by time. Okay. Now, how long did it take us to complete 1.5? 1.5 is 1.5. It took us 0.03. But I can tell from this, because this is a nice scale. This is 0.01. This is 0.02, right? Now, we are looking for frequency there. So if you go to your calculator and say 1.5 divided by 0.03, okay, that's the time. This gives us 50, right? This gives us what? 50 hertz. Okay. Now, this is, so the formula mark is not there. It is the mark for substituting correctly. Now, period, according to this graph, our period is 0.02 seconds. Okay, let's break it down. What do we mean when we say our period is 0.02 seconds? It says for this AC source or this AC generator, it takes us 0.02 seconds to complete one full cycle. And we know that F is equals to 1 over T, right? So F is equals to 1 over 0.02, right? That's the period, okay? Now, 1 divided by 0.02, it gives us exactly the 50 hertz that we spoke about. So this goes on to prove that indeed the period is not 0.02 and the frequency for the same source is actually 50 hertz. What does it mean? It means it completes 50 complete revolutions in 1 second. That's super fast, right? That's the frequency. So there are many ways to actually do it. I hope it makes sense. Right. Okay. Now, the AC generator is something that is of particular interest for us for the purpose of today's session, right? Potential difference is maximum. This is Vmax when the coil moves past the horizontal position. We explained that. I'm going to recap once again. If this is the plane of the magnetic field between those two permanent magnets, and the coil is lying like this, and it's rotating in that way, okay, whether clockwise or anti-clockwise. Now, what is actually happening? The ends of the coil are moving perpendicular to the invisible magnetic field. That's where we induce the maximum EMF and the maximum current. So the current associated with that position will be your I max, which is obviously related to V max, which is the peak voltage, right? That's the most important thing. Okay, so when the coil moves past the vertical position, the rate of change is 0. So what do we mean when we say the rate of change of magnetic flux linkage is 0? It means at that particular position, the coil and the magnetic field are not interacting with each other. So once the coil or the conducting material does not move across or disturb that magnetic field, there is a zero rate of change of magnetic flux linkage, right? That's where we get the zero EMF, okay? Right. That's the most important part that I wanted to explain, right? Now, if you check at time zero, okay, at this time, the coil, this is the magnetic field. So our magnetic field is from north to south based on that direction that you are seeing there, all right? Now, if the coil is in that plane, this is the coil, it is lying perpendicular to the magnetic field, hence it's moving parallel to the magnetic field. There is the field, there is the movement of the coil, there is the movement of the coil. It's moving parallel to the field, it's zero. But when it's lying on a horizontal plane, parallel to the magnetic field, we induce the maximum. So this is our, in other words, this is our V max, right? This is still the same V max, but in the opposite direction. So this is negative V max, right? So that's basically the alternating output for induced EMF, or even the shape of the induced current remains as such. Okay, right. Now, one other practical aspect of alternating current generator is the fact that it is actually having a lot of real life applications, right? It says here AC generators are used in electrical power plants. So where there's an electricity generation on a large scale, where we want to get mega and megawatts of energy, we are using the AC because it generates, because the DC is relatively smaller output. Okay, so it uses diesel. We put a lot of energy. Diesel is costly. We use coal, to turn the turbines, something that we would have maybe discussed in grade 9. Okay, so now we're converting kinetic, which is a form of what? Mechanical energy, okay, into electrical. So we accept that in a generator, mechanical energy, whether it's AC or DC, mechanical energy is converted to electrical energy. Okay. This is a giveaway question that's most likely to be asked. So you need to be able to actually recall that. Okay. In cars, which is, in modern day automobiles, cars have become more than just a luxury. It's a necessity because it is a mode of transport. It makes life much easier. So cars recharge the battery while it is being given. So the name of the generator, or the AC generator that is used in a car in this case, is actually an alternator. Okay, I think it comes from the word alternating current. Okay, so this is an alternator. So an alternator becomes the device in the car. That's why the car has to move. That's the mechanical energy. So while it's moving, the alternator generates that electrical energy, which is stored to actually propel or drive multifunctions within a car, right? And then in the moving coil in microphones, we also have an AC generator there. And then DC generators on a small scale, you make a comparison. It's used in a bicycle dynamo. So a dynamo is a DC generator. Okay, so what is happening here, just to break it down, we've got a small generator that is upright like this. It's in contact with the rear wheel of the tire of the bicycle. So as the wheel moves, it is spinning that magnetic field, which generates the current and EMF that it makes the light bulb or the lamp of the bike or the bicycle to actually go on. So it's a small type of a generator. It's based on the purpose or its application. Torches and battery chargers, they use DC generators. Right. Okay. Now, I want us to look at this worked example and take a discussion on that. I'll try and break it down as easy as I possibly can, so that you understand also the technique in which you look at the problem statement, do the routine calculations, respond to basic remembering or recall type of questions, and also paying particular attention to the mark allocation. That's the sole purpose of this worked example. So I just want you to pay very close attention. Do not write, so that you have a sense of what we are talking about in this case. It says here, the maximum voltage produced by the generator is 125 volts. Okay. Now, that statement carries a lot of data that's going to be important moving forward. Now, we have to classify that voltage. Okay. So, in other words, we know that V max, this is the peak voltage, is equals to 125 volts, right? Then it says define the term. The action word is define. Okay, root mean square voltage, right? If you define, number one, you need to pay careful attention to the keywords. That's number one. Use the keywords in the correct context. What exactly do we mean by that? When you write the keywords in your definition as you remember it, when I read that definition, it must carry the correct scientific meaning. Okay, right. What do we mean when we talk about the root mean square voltage? This is the alternating current voltage which dissipates the same amount of energy as the equivalent DC voltage. So I can go back to our examination guideline there, because that's our point of reference, right? We can go back to our examination guideline so that we understand where we're coming from. It says define the root mean square voltage. The root mean square voltage, which is potential difference, is the AC potential difference. What is this voltage for? Is it for DC or for AC? It is the AC potential difference, or the AC voltage that produces the same amount of energy as an equivalent DC potential difference. Okay, so you need to capture the keywords. The root mean is the AC potential difference produces or dissipates same amount of energy, equivalent DC voltage. So those are the key terms, right? So for this definition, it's either you remember or you don't. Hence, it's going to be 2 marks or nothing. Okay, that we have to put it in context so that you understand that definition are by far the easiest or the most straightforward questions that you may get in an exam, right? And then that's why it's 2 marks. So it's either 2 out of 2 or 0 out of 2. Okay, but you are supposed to get the 2 marks because it's just remembering. It's not even rocket science, right? And then calculate, that's the keyword, the root mean square voltage of the generator. VRMS equals to question mark. So if we go to, we know that V max is equals to 125 volts. Okay, we are looking for VRMS. And if it's 3 marks, number one, refer to the formula sheet. Identify the correct formula, copy it, including the subscripts. Substitute correctly. Carry out the calculation using a calculator. Show all the substitutions and show all the calculations. Include the correct SI unit. Those are the key things. So we know from the data sheet that VRMS is equals to V maximum divided by root 2. 1 mark for that. So VRMS is equals to, let's verify that value is 125 volts, correct? Is equals to 125 divided by root 2. Okay. Some prefer to leave it like that, but we can actually evaluate that. It's 125 divided by root 2. Okay. Okay, it's 88,39. 88,39 volts. Right. Also, what is important in this case is to pay attention to the number of decimal places to which you round off the final answer. So this is the correct value of voltage. This is the actual value, but this is correct to 2 decimal places as per the instruction. Okay. So round off your final answer correct to the nearest 2 decimal places, unless or otherwise stated. So I would want to draw your attention once again to the instructions so that you understand where this is coming from. Okay, let's go back. Okay, it says the total resistance in the external circuit. Now, what type of a circuit is this? This is a purely resistive circuit. Okay. Take note, this is what the exam guide say. The total resistance R is equals to 42.4 ohms. Calculate the maximum current. There we are. Okay, 3 marks. Formula, substitution, answer. Okay, we are looking for the Imax, right? Okay, so if we are looking for the maximum current, we can safely use even the Ohm's law, right? The Ohm's law says I is equals to V over R. Is it fine? But here we're talking about the maximum current or the peak current, which is related to the maximum what? Voltage. So 1 mark for that formula. Maximum current is equals to 125 divided by our resistance, which is 42.4 ohms. All right. Okay, this is 42.4 ohms. Right. All right. So if that's the case there, we are saying, therefore, if we can move to the next one, it's gonna be, in this case, our Imax is equals to which is 125 divided by our resistance, which is 42.4. Okay, so if we say 125 divided by 42.4, okay, 42.4, okay, this gives us a value of 2.95 amperes. 2.95 amperes. So this is not what is delivered to the circuit. What is delivered is actually the main current, which is the root mean square current. Right. So that's 3 marks for that formula, substitution, and answer. And then we're supposed to sketch a graph of induced current versus time. Okay. The graph is of induced current versus time. Okay. For 2 complete rotations. So this is an AC graph. Okay. Indicate the time. Okay. There is a horizontal axis. Okay, that's the time in seconds. Okay, so the generator has a frequency of 20 hertz. So if it's 20 hertz, the period, therefore, is equals to 1 over 20. Okay, so if we say 1 over 20, we get a period of 0.05. 0.05 seconds. So it takes 0.05 seconds to make 1 complete cycle. Where did we get it? We got it from the frequency, right? So the time taken for 2 rotations, so that's 1 rotation, that's 2, okay? So if 1 takes 0.05, it means 2 will take 0.1. This is time in seconds, okay? Because this is 0.05, okay? And then the maximum current induced by the generator. So this is current in amperes. That's 0 there. So our maximum will be negative 2.95 in the other direction, and then positive 2.95. So the magnitude of the peak current is actually the same, but in opposite direction after every half cycle, because it is indeed a typical example of an alternating current generator. So these are the typical questions that we have discussed in our worked example, which is going to lay foundation for the other problems that I'm going to give you an opportunity to try and work on as individuals. Some you try and attempt those as a group or whatever the case may be. But basically, this is what is required when you say you have done purely resistive circuits, which will take turns to also look at after the short break. Let's take a 5 minutes break and see you after that. Welcome back, grade 12. We're still on our live session for physical sciences. We are focusing our attention on alternating current. So before we went for a short break, we managed to look at a practical example of the type of questions that can actually be asked when it comes to, AC generators and purely resistive circuits. Right. Having said that, I think we also took note of the fact that there are very important formulae from grade 10 that we must remember, that period is actually the reciprocal of frequency, and frequency is the reciprocal of period, right? So that is something that you must always remember. Okay, so where period is the time taken to complete one cycle, the time it takes the coil to make one complete revolution. That's number one. And then the frequency, we are asking ourselves that how many complete revolutions do we manage to get of the coil in a second per unit time? So if we say an AC generator has a frequency of 50 hertz, as we'd have seen in the example that we did earlier, we are meaning it says to us that there are 50 complete cycles or revolutions of the coil in the magnetic field in a second. That is per unit time. Now, it is the time for us to try something as individuals. This is a very nice type of a question because it would not only test our understanding, but also our remembering in terms of, the use of the data sheet as well. When we carry out the routine calculations. So the next question is based on a coil that is rotated in a magnetic field. The varying induced EMF, the moment it says induced EMF, obviously think of it in terms of an AC generator, right? Is obtained in the graph as shown below. I'm going to give you 5 minutes to try and attempt these 3 calculation questions, because these are the typical questions that you must actually get all the marks, if not most of them, right? So I'll give you 5 minutes starting from now. Welcome back, grade 12s. I hope you've made your attempt for this very short structured question with an intention to try and demonstrate our understanding. So we'll take it step by step and go over what we refer to as our possible answer, and also pay attention to what are the important things when you respond to questions of this sort. Okay, so we're told that the coil is rotated in a magnetic field, right? Which is a generator. The varying, this is the change or the fluctuating induced EMF obtained, is represented in the graph, right? So this question has to do with interpretation, okay? So we want to apply our skill interpretation of graph. Okay, this is one practical example of interpretation of graphs. It says calculate, okay, 3 marks. Formula, substitution answer. The induced root mean square potential difference. Okay, what are we looking for? We're looking for VRMS. All right, now we have to obtain data from the graph itself. Okay, so what is our peak voltage? Our peak voltage is 1 volt. This minus, it says in the opposite direction, 1 in the other direction. So we know that our maximum voltage, which is our V max, we read it off from the graph, is 1 volt, right? And then what does the question require of us? It wants us to calculate the root mean square potential difference, right? So what is this? We're looking for VRMS, which is the root mean square voltage, is equals to V max, which is the peak voltage, over root 2. Okay, that's as easy as it gets. So it's going to be 1 over root 2. All right? What is 1 over root 2? Okay. 1 divided by root 2. Okay. Which is root 2 over 2 volts. Okay. So that is like 0.71. Okay. 0.71 volts. This is our VRMS. Okay. VRMS. So it means what is delivered to the appliance, if this is connected to a purely resistive circuit, it's not the 1 volt, which is the peak or the maximum current voltage. In this case, it's going to be the 0.71 volts. So 1 mark for copying the formula, 1 mark for substitution correctly, 1 mark for the correct answer, including the SI unit, and always 2 decimal places. Right? Don't forget that. Okay, and then the follow-up question says the coil is now rotated at twice the original speed, right? It's twice the original speed. Now, if you look at this, there is this graph, there is 1 complete cycle. Okay, so if this is 0.02, this is 0.04, 0.06, then this is 0.08 seconds. So what is this 0.08 seconds? We can immediately appreciate that the period in this case is 0.08 seconds. What does it mean? It means for a coil to make 1 complete revolution, it takes a period or a duration of 0.08 seconds, right? Now, from this, we can know that the frequency is equal to 1 over this period, okay? Which is 1 over 0.08. Let's quantify the original frequency. 1 divided by 0.08. Okay? This gives us 12.5 hertz. 12.5 hertz. All right? What does this mean? It means it does 12.5 oscillations or cycles in 1 second. So this is like 12 hertz. 12.5 hertz, okay, is 12.5 hertz is equals to 12.5 cycles per second. That's what it means. It's not us, but we're trying to put a meaning to what is this. Right, now it says write down the period of the wave. So the period, we can read it off from the graph there because we've interpreted the scale. So the period of the wave is t. So t is equals to 0.08 seconds, right? Just for writing that, you'll get 2 marks because you have to read it off from the graph, make sense of the scale, right? Okay, and then the follow-up question says, calculate the average power. Okay, this is P average, generated by the generator if it produces a maximum current of 2 amperes. So what do we know? We know that I max is equals to 2 amperes, right? So we know again that P average, okay, average, which is P average, is equals to VRMS, which we've calculated there, multiplied by IRMS. But now we don't have IRMS, but we can find IRMS by saying I max over root 2. Okay, so IRMS is equals to 2 over root 2, right? Amperes, whatever that is. Okay, so P average, if we substitute now, is equals to 1 over root 2, okay, which is the 0.71, right? Okay, we multiply this by 2 over root 2, right? Okay, I'll round off at the end. So P average, therefore, is equals to, if you say root 2 times root 2, it's going to be 2. And then 1 times 2 is 2. So it's 2 over 2, which gives us what? 1 watt. Okay, so the average power in this case is 1 watt. Watt, it means 1 joule of energy per second. Right, so this is, if I can go back, if it's 4 marks, it means we had to, first of all, given the maximum current, we had to calculate the root mean square current. Right, so that's a practical example of questions that involve these type of calculations. Right. Okay, now this is a second activity that I want us to also try. I will give you 5 minutes to try this activity, and then this is a typical example of a purely resistive circuit, because instead we've got not just a resistor, it's a cable. Okay, it's a resistor, you can check that. Okay, that's a resistor which is connected in parallel to a toaster, which is another resistor, right? So these are 2 resistors, or actual appliances. So it says the circuit diagram below shows an electric kettle and a toaster. These are resistors connected to an AC. So the source is not a DC source, it's an AC source, as you can see. So the 220 that is given there, we must understand it in the context of a purely resistive circuit, which has got a source of an AC, right? And then we are told that VRMS is 220. So if we connect a voltmeter there, we'll get the 220 volts there, okay? The ammeter and the connecting switches have negligible resistance. So the only resistors in this circuit is the kettle and the toaster. Okay, so I'll give you another 5 minutes to attempt this question, and then we'll take a discussion from that point on. Your 5 minutes starts from now. Welcome back, Kratos. I hope you've made your attempt on this structured question, which obviously consists of your straightforward basic recall, which is the definition, which tests your remembering skills, and then also managed to carry out the routine calculations. Right. So this is a practical example of what would be referred to as the purely resistive circuit in the context of alternating current. So the 220 volts is the VRMS. So we are saying VRMS is equals to 220 volts, right? Then it's given. So we are collecting the data there, it's given. And then the only resistors in the circuit in this case is the kettle and the toaster. Now define the term root mean square current, right? So if it's not root mean square voltage, it's most likely root mean square current. So this is the alternating current, right? Which of an AC source which dissipates the same amount of energy as the equivalent DC. Okay, current. So that's basic recall is either full marks or nothing, right? And refer to the exam guide for the keywords, right? Or else refer to the examination guidelines, right? When switch S1 is closed, we close switch S1 like that, and switch S2 is open. What does that mean? When switch S1 is closed and S2 open, the only resistor in the circuit in this case will be the kettle. There we are, right? Okay, then we are told that the maximum current, Imax, okay, is equals to 3.6 amperes. Calculate the root mean square current in the circuit. Calculate the root mean square current in the circuit, right? Because we don't know the resistance of the cable, but we know the peak current. So if it's 3 marks, it's going to be your typical formula, substitution, and answer. So we are saying okay, let's go back. We want a root mean square current, okay? So IRMS is equals to peak current, which is the maximum current, over root 2. Do not forget the subscripts, very, very important, okay? So IRMS is equals to what is our maximum current that we are given? We are told that is 3.6 amperes. There it is, right? So it's going to be 3.6 divided by root 2. So our IRMS, we can go to the calculator. It therefore says 3.6 divided by root 2, right? Okay, it gives us 2.55, okay? 2.55 amperes. So this is our root mean square current. So 1 mark for the formula, 1 mark for the substitution, and another mark for the correct answer, including the correct SI unit. So always refer to the data sheet so that you are able to correctly copy the formula, right? Okay. Now we are told that when switch S1 is open and switch S2 is closed, we open S1, okay, and then we close S2. It means the only resistor in the circuit is this one, which is the toaster, connected in series. Okay, so whatever current the root, so this ammeter will register the root mean square current because this is VRMS, right? Okay, and then the root mean square current is 2.62 amperes. Okay, let's collect the data. Now this is about the toaster. Okay, so root mean square current I RMS when switch S2 is closed and switch S1 is open. Root mean square current, we're told, is 2.62 amperes. Okay, 2.62 amperes, right? Then it goes further and says, calculate the energy consumed by the toaster in 2 minutes, right? Now, we want the energy. So energy is W, okay, which is work, because work is energy and energy is work. So when work is done, the toaster converts electrical energy into heat, right? By so doing, it is doing work. okay? Because the toaster is to heat the bread or whatever, but the temperature must rise. So this is a resistor that converts electrical energy into heat. We're looking for W. We've got the root mean square current, right? We also have the root mean square voltage because the toaster is the only device. But then the time must be in seconds. So 2 minutes is 2 multiplied by 60 seconds, which is equals to 120 seconds. Excuse me. So W is equals to V I delta T, right? So that's W, okay? But now this work done is equals to V RMS because that's the potential difference across the toaster, the current through delivered from that AC source multiplied by the time. So in other words, this is the formula that we're interested in, okay? So W is equals to 220, okay, multiplied by 2,62 multiplied by 120, okay? So energy or work done will be in joules, right? So it's 220 multiplied by 2,62 multiplied by the time, which is 120 seconds. So it's 69,000, okay, 168 joules. Okay, that's how we get to that. So the conversion there would give us the 2 marks in the substitution, the formula, and the correct answer, which gives us a total of 4 marks. Right. So pay attention to that. So this is actually, or if it's 3 marks, it means it's formula, substitution, and answer. Okay. So pay attention to the mark allocation there. Right. So this is a practical example of what, in essence, is a purely resistive circuit. Now, what is also important with this particular circuit, the knowledge from grade 10 and 11 that if a component is connected in series, the current passing through the source is equals to the current passing through that resistor. So if the kettle is the only appliance connected in that purely resistive circuit, what therefore that means in this case is that the VRMS is actually the voltage across the toaster. So if we connect V there, it will read 220 volts, okay, provided this switch is open, all right? So the 220, which is the one that's the terminal potential, or is your equivalent terminal potential difference, is what is delivered. So this is VRMS, okay, which will be marked there. Right. So also take note, if a question is more than this was supposed to be 3 marks, okay, because it's the entire substitution that must be correct. Right. Okay. And then a very quick one that I want us to try this is a homework activity. But what I'm going to do now, I'll try and guide you through it first so that you understand what you have to do. And then you'll use this as a practice type of an activity at home after the session, right? But let's go through it so that we understand, because there's more to it than just, a routine calculation, plugging in values and using a calculator. We've got a resistor Y, which is rated 220 volts, right? And then the AC source is also 220 volts. So this 220 volts is actually the root mean square voltage, right? Then it's rated 100 watts. Okay, this is the wattage of this. So this is 100 watts, right? That's the power rating of this resistor. It's connected to a 220 AC source. That's the source. So the 220, this 220 is actually the VRMS, right? Okay, as shown. Now they want you to calculate the resistance of resistor Y, right? We know it's a power rating. So P average, because it's the average power, is equals to 100 watts. It's given. Okay. We also have VRMS, okay, which is equals to 220 volts. Okay. And then the question wants us to calculate the resistance of Y. Okay, straightforward. Y is the only component connected to this AC source. Then it goes further and says another resistor Z with a rating, same rating, but unknown watts, which is the power rating, average power rating, which is X. Okay, right? Is now connected in series. So what does that mean? The current through resistor Y is equals to the current through resistor Z. But do not forget, the two resistors, X and Y, they actually V across Y plus V across Z must give us the what? The 220 volts. Okay, where is this coming from? If two resistors are connected in series, we refer to them as potential dividers. So the root mean square voltage of 220 volts is split or is divided between resistor Y and resistor Z. That's why if you add that potential difference of the source of Y and Z, it should give you the 220, which is the VRMS. Now we're told that the power dissipated by resistor Y changes to 80. It changes to 80, not by 80. So the new power in this arrangement of resistors, in this purely resistive circuit for Y is now 80 watts. Okay, it's now 80 watts. Okay, it was 100, now it's 80. It changes. Okay, so it's no longer operating at maximum now because of resistor Z. Now they want us to calculate the power rating of resistor Z, assuming that the resistors have got a constant resistance. So the resistance of Y did not change. Okay, it's only the power that it dissipates. So that's the long and short of this question. Try and apply your knowledge of simple circuits. What happens to resistors in series? Let's appreciate the fact that current is the same through resistor Y and through resistor Z, right? And then what else do we know? If we have got the power rating, the new power, the energy dissipated by the power dissipated by resistor Y, we can determine the current, which will be the same current as that of what? Of Z. And then we know the 220 now is not just for resistor Y, it's for both resistor Y and resistor Z, whose sum of the potential difference is the root mean square voltage of 220. Okay, so it's a little bit a notch higher because it's a multi-step question with a mark allocation of 6 marks. Right. We would love to go on and on, but I have to leave this with you as a take-home activity. Then you will obviously discuss it with the teachers and they will obviously guide you on this. Because of time constraints, thank you for joining us for a live session. From myself, Temba, have a pleasant one. See you next time.